Well, hello, my name is Dr. Nzinga Mack, and I'm going to be talking to you today about how wonderful computational modeling is. And we're going to be taking a look at accelerating translation of immune targeted treatments. But first, let's take a look at some of the ideas that are going to be behind why you want to accelerate these particular types of treatments. So as you can see here, you have this eureka moment in the lab, your treatment has worked. So now you have a couple of things to figure out before you can get it to a patient. So for example, you have to figure out how you should administer this treatment to people. You need to figure out whether or not it's safe. You need to figure out whether or not it's effective. And you also need to think about the potential side effects of the drug in people. So we have to figure out a way in order to really make sure that we can accelerate this process. So one of the ways that we can do this is by building a computational PK/PD model. And we'll get into more about what that PK/PD model is a little bit later on. But for now, let's talk about how we build that computational model of these particular treatments. So one of the things that you want to think about is the treatment itself. The IL-2 treatment was engineered and tested by Dr. Jamie Spangler and her lab. And you can take a look at them here. And we also know that we need to build this computational model. So I'm building this computational model along with Dr. Phelan McGowan and his lab. After we built the computational model, we validated it against experimental data, and then we're going to expand it to that PK/PD model. So let's get into a little bit of detail about this IL-2 treatment. IL-2 is very powerful as a treatment. However, there are a couple of problems. So one of the problems is that when you give IL-2 by itself, it acts on effector T cells, and that's going to send the immune system into attack mode. And that's useful in certain types of cancer when you want the immune system in attack mode. However, at the exact same time, in the exact same person, if you give IL-2, it's also going to act on regulatory T cells, and those are going to rein in the immune system. Of course, that's useful for the treatment of autoimmune diseases. So the problem is when you give IL-2 to a patient, at the exact same time, IL-2 is going to be having these two polar opposite effects, and that can actually drive the pathogenesis of the disease that we're trying to cure, which is horrible, right? So the idea is, well, how do we fix this? How do we specify which particular pathway IL-2 is going to take? So that's exactly what Dr. Jamie Spangler and her lab did, that they engineered antibodies that they tethered to IL-2 to make these immunocytokines that have these two opposite effects. So if you take a look at this F10 immunocytokine, you can see it's comprised of this F10 antibody that's tethered to IL-2. When it comes to the F511 immunocytokine, you can see that it's the F511 antibody tethered to IL-2. Now, the F10 immunocytokine sends the immune system into attack mode, right? Whereas the F511 immunocytokine is going to rein in the immune system. Okay, great. So we have this wonderful treatment. So how are we going to make it into a computational model? Well, one of the things that you do when you're building a computational mechanistic model is that you have to think about the biology of the system. And when you think about the biology of the system, and we'll back up for a second, one of the things that you want to think about is, okay, how do I represent the biology? Well, you represent the biology by looking at the chemistry, the chemical reactions that are happening as a result of the biology. So then you have to think about, okay, well, how do I represent the chemistry? Well, how do you represent the chemistry? You represent it with mathematical equations. And that's exactly what we're doing in order to build these computational mechanistic models of this IL-2 system. So while we're doing that, we have to think about, well, what are the major players? And we have about 15 or so of these major players. I just have a couple here. IL-2, IL-2 receptor alpha, beta, gamma. You also want to think about, okay, well, we want to traffic these particular molecules, these ligand receptor complexes. So when we think about trafficking, we have to think about things like internalization of the ligand receptor complex. We have to think about recycling, degradation, production. And what we basically are doing is that we are writing rate law equations for each one of these particular reactions for each combination of these molecules, right? So we have about 30 of these parameters that we're dealing with, and we have about 15 of these molecules. So then the next step is to make sure that we write ordinary differential equations that we're using to track the concentration of these ligand receptor complexes at any given point in time, right? And by the way, there are about 40 of these equations that we wrote in this particular model. So here's a sample equation. So one of the equations that you see here, we can actually expand it because each one of these terms is an expanded version of this equation that looks something like this. The equation is actually a little bit more complex than that, but I simplified it for this particular presentation. But the bottom line is, if we want to think about what this equation is representing, we're thinking about the binding of this ligand receptor complex. We're thinking about the recycling. We're thinking about internalization, and we're also going to be thinking about degradation. So we did all of this, wrote all of these equations, considered all of these parameters, considered all of these molecules, and then we made sure that we wrote code to simulate the cell in its normal state before IL-2 is added to the cell. And then we simulated IL-2 being added to the cell. Well, unfortunately, the initial simulations didn't go all that well. And part of the reason why was because we had an assumption. And one of the rules when we're making these computational models is that we try to make it as simple as possible, but still represent the biology. When we're finding that it's not representing the biology, then we add some more complexity that's reflected in the biological system. So this is a prime example. So if you take a look at this, we were assuming that the concentration of the ligand receptor complex was equal to the concentration of activated SAT5. And we were using activated SAT5 as a proxy for cellular activation. We were assuming a 1-to-1 ratio. And when we did that, this is the data that we got. So let's take a look at this. The green are the dots, the green dots. These are the T effector experimental data that Dr. Spengler's lab produced. And then the lines, the green lines, are the T effector simulation data that the simulation produced. As you can see, the amount of IL-2 that was necessary to reach max activation in the simulation, if you only focus on the green, was much higher than in the experimental data. And we found the same thing when it came to the T regulatory data as well. Okay, so how do we fix this? So we have to change some of our assumptions. So one of the things that we said was, you know what? Well, maybe there isn't a 1-to-1 ratio between ligand receptor complex and activated SAT5. Maybe there's an element of cooperativity. And that's exactly what we tested. We used the Hill function in order to add an element of cooperativity into this. And the N is your cooperativity coefficient. So we said, okay, well, now we reran the simulations and we had an absolutely wonderful match with the experimental data from Dr. Spengler's lab and our simulation data. Same thing when it came to the T regulatory data. And even more excitingly, we had a wonderful match when it came to the immunocytokine data, the treatment data. So the idea is, okay, where do we go from here? So I'm going to expand the model to the F511 immunocytokine. And then I'm going to start thinking about PK/PD, pharmacokinetics, right? If we're thinking about pharmacokinetics, that's what the body is going to be doing to the drug as we absorb it, distribute it, metabolize it, excrete it. And then pharmacodynamics, what the drug is going to be doing to the body, what you wanted when you came up with your treatment in the first place, right? And the way that we're going to expand it to PK/PD, just as we track the concentrations of the immunocytokine in order to come up with the initial cellular computational model, now we're going to track the concentrations of those ligand receptor complexes as they go throughout the different compartments, as they go throughout the different organs in the body to make that PK/PD model. I always say, I'm trained as a pharmacologist. I always say that every single person who comes up with any treatment, you all have to come back to the pharmacologist. You all have to go through us before you can get that treatment to the public. And this is exactly what we're doing here. Now, the wonderful thing about these computational PK/PD models is that they can inform the animal models, and that saves tons of time and tons of resources, especially if you're thinking about something like a worldwide pandemic, and you're trying to get a treatment out to people as quickly as possible. Computational work was used in order to help approve the COVID vaccine, the Pfizer COVID vaccine in Europe. So this is definitely something that you should think about and consider. Bottom line, computational modeling is absolutely wonderful. We know that we can use it in order to get these treatments to our patients that need them a lot faster, any treatment. Well, thank you for your time and your attention. I'd like to acknowledge the Spangler Lab and the McGowan Lab for all of their help with this work. Questions, comments? Oh, okay, question.
So when you say you want to expand your model to the to encompass PKPD, do you mean like your model is going to be nested within the PKPD model, as in like you taking all these additional variables and add them on top? So where you have your model tracking at the cellular level within a model tracking at the like body and organ level, or do you mean you're going to like use the framework for your model and essentially change the variables to then be like, okay, on a whole organism model, the variables, these are the equivalents?
The former. So
Okay.
what my model is doing now is tracking where these particular ligand receptor complexes are in the cell. So now I'm going to say, okay, let's expand it out to different compartments and say, okay, well, if we are injecting this particular treatment, okay, well, what is going to be the amount of ligand receptor complex is going to be in the bloodstream? Okay, let's think about the kidney. Let's think about the liver. So we're going to be tracking where these molecules will be in the liver. We're also going to be thinking about the pharmacokinetics, like what the body is going to be doing to these ligand receptor complexes, and what is actually going to be the drug that's going to be left once it's actually going to be working at the way that it was designed to work to have the activity that it needs to have. So we just kind of expand, like, okay, it's in the cell. Okay, what's it doing in the blood? What's it doing in the kidney? What's it doing in the liver, etc. What's it doing in the brain or wherever it's supposed to go? So another hand question. Okay, well, thank you very much.
I just want to comment that you did a really, really nice job taking something that's very complicated in terms of the model and distilling what we need to get out of like its utility. So that was fantastic.
Wonderful, thank you.
Thank you.
Appreciate it.